All right, morning. These are the notes concerning the notes that you should already have copied down again and put in your notebook, and then sent me a picture already. And it is to comparing the element, compound, and mixtures. All right, they look like this. It was like a little chart. So I'm going through this. What we are going to do is I'm actually going to work my way across on each one of these as we describe them. So I'm not going to go vertical on these. Instead, I'm going to go sideways because we're really comparing each one. We're comparing the element to the compound to the mixture. So the first one there, when we look at elements cannot be separated into smaller substances. They all have the same properties. If I use my ring, this ring is made out of an element titanium. So all the atoms that are in here, they're all exactly the same. The atom that's on this side, the atoms on this side, all of them are exactly the same. They can't be separated. I can't take this atom of titanium that's in here and separate it and make it into anything new, right? It's as small, that's as small as I can possibly go, and they have all of the same properties all the way through. This titanium atom here and the titanium atom on the other side are both exactly the same. Now we go to the middle part of the chart, compounds. Compounds can be separated, but only by chemical means, like the idea of water. Well, water is made up of two elements. It's made up of hydrogen and oxygen. And we have a little formula, hydrogen H2O, and that's the formula for water. Well, those two elements are combined chemically. They're put together chemically. It's really, really hard to get them apart. The only way you can get them apart is you have to run a lot of high electricity through it. And that will actually take the hydrogen and the oxygen and separate them. And I can get hydrogen all by itself, and I can get oxygen all by itself. That's not considered to be an easy process in order to run that electricity through the water, which is very, very dangerous anyways. But that's the only way we can get them separated. So those a compound can be separated, but by chemical means. Now, if we go to the last column, which says mixtures, mixtures can be separated by physical means. In the last set of notes, when we talked about mixtures and the whole idea of being able to separate muddy water, all we got to simply do is let it sit, and the mud will settle to the bottom, the water will stay at the top, and we can actually take the water off the top of it and leave the mud in the bottom. Which is one of the ways in which they separate the nasty stuff out of the water that we drink in cities, is they put them into big pools, they let the heavy stuff sink to the bottom, and they take off the top little bit of water. And that allows them to just get clean water off the top. And then they collect the nasty stuff off the bottom. Which is actually, if you've ever gone by the water treatment plant, which is over on Ben Oak, there's like this fenced-in pond underneath the walking trail bridge. And you look at it and you go, oh my gosh, that pond is nasty. It's all white. Looks like it would glow in the dark late at night. That pond is actually what it is. It's really the settling stuff that they get when they clean the city water that they're taking out of Lake Hadron. And they send it over there, and they actually then collect it. It has lime in it, and then they sell that to farmers to spread on their fields to help neutralize the acid content of the soil. And they can get the acid content in the soil become more neutral again so that they can grow crops better. So it is actually a useful place. Right? It looks really gross, but that's what it is. It's just the sediment from the water. So elements cannot be separated. Compounds can be separated by chemical means. Mixtures can be separated by physical means. So those are the three things going across the top. Now let's go to the second row. Second row, looking underneath the element, it says they can be represented by one chemical symbol, like this, hydrogen. That H is a symbol for hydrogen. The O is a symbol for oxygen. HE is a symbol for helium. Now, where do you find these symbols? Well, you find it on a periodic table. What you are going to need to do, if you're at home, you're going to need to do a Google search. And what I want you to Google search is periodic table. And you should be able to bring up a periodic table from somewhere, and then you are going to need to utilize that. I actually have up above me is my periodic table. Right up there, that's my, right up there, that's my periodic table up above me that I have in class to reference all the time. And we will be referencing the periodic table a lot in class. So you are going to want to get one, download it, and then possibly print it off or save it on your computer so that you can reference back to it all the time. That periodic table lists all the elements. It gives you all the symbols, it gives you their names that you're going to need to do for the homework coming up. Those symbols are either, if it's just one letter, then the first letter, that letter is capitalized. like the H and the O. If it's made up of two letters, like in the example HE in the notes, that's helium. If it's two letters, the first one's capital, the second one's lowercase. It's very important to do it that way. Don't make it capital H, capital E. Then it looks like two separate elements. It's got to be capital, lowercase. Now, there are some elements on the periodic table like sodium that starts with SO, but its symbol is Na. That seems weird. Why in the world is it Na? Why don't they use SO? Well, S was already used for sulfur. Now, why didn't they use SO? I don't know. But they actually utilized the Latin name for sodium, which is natrium. And natrium is Na at the beginning. So that's how they got Na for sodium. Iron is spelled I-R-O-N. So it seems like it should be IR, but IR is already taken by iridium. So they use the Latin name for iron, which is ferrous or ferric. So its symbol is Fe. So some of the elements on the periodic table, you're going to notice that their symbols don't match up with the name that we use. And the reason for that, again, is because they utilize the Latin name. So elements are represented by one symbol. Right? And that symbol may be one letter or maybe two letters. If it's two, it's capital, lowercase. Compounds, on the other hand, are represented by two or more chemical symbols. And the two I gave you in the notes, one is water. So that's made up of the element hydrogen and oxygen. The little 2 that's there tells us how many hydrogens there are. And then there's no number next to the oxygen, so that means there's only one oxygen to every 2 hydrogens. The other one that I gave you was sodium chloride, NaCl. So that's made up of sodium and chlorine, 2 separate elements that are now chemically combined. Notice that there's nothing in between them. It shows them that they're chemically combined together. Now, a mixture is represented by 2 or more names of the substances that are in it. And what I gave you in the notes was Kool-Aid. Well, Kool-Aid is made up of sugar, water, food coloring. I did leave out in there, you could say flavoring, so it tastes like lemon, lime, cherry, grape. Those are the things that are in there. And they're just represented by the names to make Kool-Aid. So that's how we tell the difference on those 3 elements, compounds, mixtures. Let's go to the third line going across. Elements. Elements are only one phase or state of matter at room temperature. So my ring that's made out of the element titanium, it's going to be a solid at room temperature. I got to raise the temperature on that way above room temperature to get it to melt and become a liquid. So they're going to be one phase at room temperature. When you get to a compound, compounds are also only one phase. Thinking of this compound up here, water, what is its phase at room temperature? Well, it's a liquid at room temperature. You got to lower that temperature a whole bunch to make it a solid at room temperature. You got to raise the temperature in order to make it a gas at room temperature. So compounds are one phase. Sodium chloride, which is table salt, that one's only one phase at room temperature. It's always a solid at room temperature. We got to raise that temperature way up to about 7,000 degrees Fahrenheit in order to get it to the point where it becomes a liquid or a gas. Now the last one in that row is a mixture. Mixtures can be one or more phases, which we talked about in the mixture notes. We can have muddy water is made up of a liquid and a solid. Liquid water, solid mud in the bottom. So we actually have 2 phases at the same time. So they can have 2 phases. If it's a solution like pop, then it's all one phase. So they can be any combination of things. All right, last row going across, elements. Elements have very specific individual physical properties. My ring, my titanium ring, is really, really hard. It's really, really heavy. Right? Those are some of its physical properties. Those are very unique to the titanium that my wedding band is made out of. If my wedding band was the other one I had, which was gold, well, it would be gold in color. It would also be really heavy, but it'd actually be really, really, really soft because gold is really soft. And that's why my ring, if you remember in the other notes, it was 14 karat instead of being 24 karat, 100% gold. They mixed it, made an alloy out of it, so at least it was a little bit harder so that it tried to stay its shape like it's supposed to, even though it's still distorted and got a weird shape, and ultimately that's why I ended up having to cut it off because it wouldn't even come off my finger. Compounds. The unique thing about compounds is the specific individual physical properties of them. They change when you put the elements together. So this substance up here, we already said at room temperature, it's a liquid. But the 2 elements that are made up, that it's made out of, if we separate those, Hydrogen by itself at room temperature is a gas. Oxygen at room temperature, it's a gas, right? But we put the two of them together, then all of a sudden it changes its property. Now it's a liquid at room temperature. Okay. Another one on that is the other one that we have there, which is sodium chloride. That's table salt. The interesting thing on sodium all by itself, if you put it in water, it sizzles, starts on fire, or blows up. And the thing is, I don't know which one it's going to do. But it's actually really, really dangerous around our body because our body is mainly water. Chlorine by itself is a poison. If you breathe chlorine, breathe a little bit of it, you can get really, really sick, breathe a little bit more of it, and you can die. It's extremely dangerous. But if we take sodium and chlorine, put them together, chemically combine them, make them into a compound, then it is salt, and we actually have to have salt in our diet. 0.9% of your body is sodium chloride. You actually have to have a small amount of sodium chloride in your diet, otherwise your body won't work right. The one problem in America, we eat way too much salt. Right? If you don't ever use a salt shaker ever again in your life, you'll still probably get too much salt in your life. But we do actually need some. Right? So again, we put those two things together. The sodium doesn't blow up in water. The chlorine's not poisonous. We change the properties on it once we make it into a compound. The third area, mixtures. Mixtures maintain all of their physical properties when you put them together. An example of that is go back to Kool-Aid. Well, Kool-Aid, we put water in it to make it a liquid. We put sugar in it to make it sweet. We put food coloring in it to make it a color, green. We put flavoring in it so it tastes lemon lime. Right? So all four of the things that we put in the Kool-Aid maintain their original properties. They don't change at all. They all keep the same properties that they started with. Right? That's the unique thing about mixtures. Think of this mixture that I had earlier. Right? I mix them all together. Do they keep their original properties? Yep, it's still green, it's blue, it's red. They keep their physical properties when you put them together. Right? And that's how we can separate mixtures, is we utilize their physical properties in order to separate them. All right, well, that concludes the notes for today on elements, compounds, and mixtures. Make sure that you go out and find yourself a copy of the periodic table online. Again, all you got to do is do a Google search for periodic table, and you'll get thousands of sources for the periodic table. Whichever one works for you, all right, is great. You're probably going to want one that has the name and the element symbol on it. And then ultimately, we're also going to want some numbers on there. But I wish I could give you a copy, a physical copy to you, but I can't really get it to you. So if you have troubles finding one, send me an email and I'll help you find one. But again, just Google one and you'll be able to find a periodic table. All right, see ya. There goes my lights for today again.